Okay, hello everyone. We are in this predicament again. Whoever is out there wishing for snow days, you need to stop. Okay, so we are going to talk about covalent bonding today. So, looking at molecules that are made up of nonmetals only. So, follow along in your note package as we go through this. I'm going to ask that you attempt doing some of the homework for this. I will go through, there's going to be examples at the end of the PowerPoint that I'm going to have you try out on your own, and then we'll take that up tomorrow in class. Okay. I'm also going to post on D2L along with this. I'm going to post a video actually that I had made with extra examples for my grade 12 class because literally this same lesson gets repeated in grade 12 as a review of learning how to draw these molecules out. Okay, so it's a little bit different than what you did in grade 10, so you're going to see it's a bit, you'll notice the difference right away. Okay, so just a review. Covalent bonds is made when we have the sharing of electrons, right? So the whole purpose of creating bonds is to have a stable octet. Remember that ionic compounds, you'll have a gaining and losing of electrons in order to do the same thing, right? To have a stable outer energy level. So in this case, you have nonmetals that will be sharing electrons, and actually the term molecule is used for when we have covalent bonds. So technically, ionic compounds, right? We never say ionic molecules. It's because they don't share their electrons. Okay, so just a comparison. So here we have two nonmetals that are going to be sharing electrons, so meaning those electrons can now move between both atoms. Whereas over here we have a metal and a nonmetal, there is a transfer. One becomes positively charged and one becomes negatively charged. So remember, ionic bonds, what's holding that force together is an electrostatic attraction, right? Positive and negative attract. Okay, so just to recap, you've probably learned this in grade 10. There are some molecules that will create on their own. Like atoms will naturally attach to other atoms of their same type. Okay, so actually there are 7 of them that do not are never found on their own. Okay, they're always found together. They're called diatomic molecules, so meaning di, two, atomic, atom. So they always come in pairs, two atoms. So they are hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, and chlorine. So there's a couple of ways that you can remember it. One kind of catchphrase or acronym to help you is I bring clay for our new house. So each of those begin with the letter for the element symbol. Whereas if you were in my class or some other teachers use this as well, I use Hofbrinkel. So hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, chlorine. Now, I don't care how you remember it. I'm never going to ask you, oh, what does Hofbrinkel mean? Or what does, I just want you to be aware of, so when I say bromine, it's never just one bromine. It comes as a pair, so Br2. Or if we say hydrogen, it's never just H, it's H2. Okay, so starting to look at how this comes together. So we'll start with something nice and simple. So we have two fluorines. So fluorines come together because each one has 7 valence electrons. One electron is shared with each other. And if you notice, right, so now if we overlap those two, each fluorine has its stable octet. Now, we never keep it with the dots. If you have electrons that are being shared, we represent them with this dash line. So each dash line represents 2 electrons. So when you're counting this, it would be like you're counting 2, 4, 6, 8, right? And the other side would be 2, 4, 6, 8 when you're counting to see if it has its stable 8. Okay, so this is also referred to as a single bond. So a single covalent bond. Now, if you look at something like oxygen, where you now have to start sharing more than one electron. So oxygen each have 6 valence electrons. So what ends up happening is they're going to share 2 with one another. So in this case, we have 2 dash lines because we're sharing 2 sets of electrons. So again, this is like I'm saying 2, 4, 6, 8. 2, 4, 6, 8. each dashed line represents 2. Okay, and of course, oh, so this is called a double bond, right? So you have single bond, double bond. And then, of course, we can have a triple bond. So the triple bond is the highest bond that you can have altogether. So you can have single, double, or triple. So nitrogen has 5 valence electrons. So it's sharing actually 3 sets of electrons with one another. So remember, each dashed line represents 2. So it's like 2, 4, 6, 8. 2, 4, 6, 8. So that's a triple bond. Now, here's the big goal of today. Okay, so by the end of this lesson, you should be able to draw a Lewis structure. So what that means is you're going to be doing using Lewis dot diagrams to essentially now create molecules. So a couple of things to keep in mind. You have to realize that the only electrons we are concerned about are the valence electrons. So of course, atoms have a whole bunch of electrons. When we're drawing these structures out, we're only looking at the valence. Okay. When you have a sharing of electrons, we represent that with a dashed line. So each set of electrons, so each 2 electrons being shared, we use a dashed line. Okay, so how many electrons can be shared depends on the element. So it has to do with how many valence electrons it has. So this is kind of a little reminder for you, but to be honest, to know how many bonds it's able to make, you have to look at the number of valence electrons it has. Hydrogen has 1 valence electron, so it can only create 1 bond. Any of the halogens, so that's group 17, they have 7 valence electrons. They can only form 1 bond because they're missing 1 from their stable 8. So hydrogen and halogens are both equal. They make 1 bond. Okay? Oxygen and sulfur, so basically anything in oxygen's column, group 16, has 6 valence electrons. So it can make up to 2 bonds because it needs 8. So it has 6, it will gain 2 by sharing. So that can come in the form of 1 double bond or 2 single bonds. Okay, so it can be a double or 2 singles, but the maximum is 2. Nitrogen and phosphorus are in the same group. They're group 15. They have 5 valence electrons, which means it needs 3 more to be stable. So it can form up to 3 covalent bonds. Now, the way that it comes, like the format, depends on what it's bonding with. So it can be a triple bond, it can be 3 single bonds, it can have a double and a single, but the point is it needs 3. Carbon and silicone make 4 covalent bonds. Again, the combination of what type of bonds it makes depends on the molecule. So it can have 2 double bonds, 4 single bonds, a single and a triple, right, adds up to 4, or a double bond and 2 single bonds. But the point is it needs to add to 4. Okay, so these are the most important rules to go through when you're completing a Lewis structure. Okay, it's going to be different from grade 10. Grade 10, you drew the Lewis dot diagrams, you circled who was doing the sharing, and then you made your bonds. Okay, that works for simple molecules. Okay, we're going to be looking at expanding our horizons in terms of the types of molecules we're drawing. The same rules that you are learning today will be the rules we will review again in grade 12. Okay, so the set of rules we talk about now will work for no matter how complex the structures get. Okay, so we're going to use CH3Cl as an example. So we're taking something simple, but the focus is to learn the rules. So number 1, the first thing you do is you have to see which of your atoms in the molecule is your middle central atom. It's always the compound, or I should say the atom that can make the most bonds. So carbon and silicone make 4 bonds. Okay, so that's the most number of bonds. So if you have carbon in your molecule, you're going to have that in the middle. The next thing you're going to do is you're going to add up all of the valence electrons that are in those elements. Okay, so literally you look at your periodic table, you figure out what group they're in, how many electrons, and you add them all together. Okay, so carbon has 4, Hydrogen has 1, but there are 3 of them, right? So that's 3 total. And chlorine is in group 17, it has 7. So it'd be 4 plus 3 plus 7 is 14. Okay, this is called our electron bank. Okay, that's more of a Miss Henson term than like a legit term, but nonetheless, 14 electrons has to be used to make up this molecule. Okay, once you have the middle carbon, you're going to put all of your other elements around. The next thing you're going to do is you're going to join the peripheral atoms to the central atom. So what that means is these electrons here that I have as my connectors have to go in first. So 2 electrons for this CH bond, 2 for this, 2 for this, 2 for that. The bonds go in first. The second location we put our electrons is right here. You're going to complete any octets on the other atoms except hydrogen. So you're not concerned about the middle atom. We're talking about the outside atom still. So the first thing is you make your bonds. Second thing, make sure the outside elements are stable. So chlorine needed 6 more. So that's why I added in these 6 here. So technically, I've used 2, 4, 6, 8, 10, 12, 14. So I've used up all 14. The last thing, or you can do this first, but for each bond where you're sharing electrons, you now replace it with a dashed line. So technically, this is my final picture. So I have 2, 4, 6, 8, 10, 12, 14. Okay, so this worked out perfectly. Like we didn't have too many electrons, we didn't have too little. Okay, so this is a situation where it's a perfect world. I'm going to show you 2 examples where it's not always going to be perfect. So we're going to do carbon dioxide. So again, same thing. You decide on which one is your central atom. So in this case, it's carbon. We're going to make our electron bank. So each carbon has 4 electrons. There's only 1 of them, so 4. Oxygen has 6, but there are 2 of them. So we have 4 plus 6 plus 6 for a total of 16 electrons in the bank. The first place you put your electrons are the bonds. Right? So I'm going to connect my C and my O. So I've used up 1, 2, 3, 4. So I have 12 electrons left in my bank. You're then going to do the outer atoms for stability. So remember, the central atom is the last place we look. So here we have 2, 4, 6, 8, 10, 12. So we had 12 electrons left. We just used them all up when we completed our oxygens. But let's do a check. Oxygen is fine, but carbon does not have 8 electrons. It has 1, 2, 3, 4. So this is a case where we finished all of the electrons from our electron bank. When this happens, you're going to then consider making double or triple bonds. Depends on what we have. So carbon and oxygen are both able to make a double bond. So what happens is we're going to actually bring in electrons from our oxygen into sharing with carbon. This next picture will show you. So if the valence shell on the central atom is not complete, okay, you're going to use a lone pair on one of the outer atoms to form a double bond. But keep in mind it has to be able to do that. So let's say instead of oxygen, if this was chlorine, okay, chlorine cannot make a double bond. So you can only do this with atoms that are applicable. So it's exactly what's going to happen here. So we're going to bring in a pair of electrons on one side and a pair of electrons on the other side. So we're not changing how many electrons are there, we're just rearranging them. So we still have 2, 4, 6, 8, 10, 12, 14, 16. That was our original number. But we've rearranged them in a way so that everything has a stable octet, right? 2, 4, 6, 8. So this happens any time where you run out of electrons in your bank, but your central atom is still not stable. You have to bring in electrons to stabilize it.